This week, we are reporting here on the lead up to Earth Day, and tonight, the alarming new report on the Colorado River.
Beneath the meandering course of the Colorado River, where sandstone cliffs and ancient rock strata tell the silent story of eons past, geologists have uncovered a phenomenon so unexpected, so urgent in its implications, that it has triggered a rare red alert, an urgent scientific call to immediate attention. The discovery was made during a routine subsurface mapping project, initially aimed at tracking sedimentary evolution in the Grand Canyon corridor. However, what began as a standard geological survey quickly transformed into a high-priority investigation when seismic imaging revealed something staggering beneath the riverbed. Before we start, smash the like and subscribe buttons for more updates. Deep below the surface, in a zone once thought to be geologically stable, researchers identified signs of a previously undetected magma body, an enormous chamber of molten rock that appears to be expanding. Nestled at a depth of approximately 25 kilometers, the structure emits heat signatures and deformation patterns indicative of active magmatic intrusion. Even more concerning are the pressure anomalies detected by borehole sensors, readings that suggest significant shifts in subterranean stress, pointing to a potential escalation in geothermal activity. This is not merely a curiosity for academic discussion. The implications of an actively inflating magma chamber under such a critical watershed stretch far beyond geological interest. The Colorado River is not only a natural marvel but a lifeline. It supplies water to nearly 40 million people across 7 U.S. states and supports massive agricultural networks and hydroelectric infrastructure. Any shift beneath its bed could pose dire consequences, not just for geology, but for the economic, environmental, and societal structures intricately dependent on the river's consistent flow. Evidence began to accumulate several months ago when satellite-based interferometric synthetic aperture radar INSAR detected minute uplift in a specific section of terrain near the river's midsection around the Glen Canyon region. At first, the displacement appeared minor, a few millimeters of vertical lift per year, nothing extraordinary on its own. But as geologists cross-referenced this data with thermal anomalies recorded by orbiting instruments and ground-based seismic readings, a pattern emerged that could not be ignored. A swarm of low-magnitude earthquakes followed, subtle yet highly localized. These were not tectonic quakes, but the kind associated with fluid migration and rock fracturing, hallmarks of magmatic movement. The seismic signatures were shallow, originating from around the depth of the suspected magma body, and they were accompanied by fluctuations in local gravity measurements. Gravimeters deployed across the region detected a slow but steady decrease in subsurface density consistent with the accumulation of lighter, molten material replacing denser rock. These signs, uplift, thermal output, microseismicity, and gravitational shifts, collectively pointed to one chilling conclusion: magma is on the move, and it's doing so in a place where it was not expected, where no volcanic system had been known before. This is what prompted the red alert, the geological equivalent of sounding an alarm. The U.S. Geological Survey (USGS), in coordination with several university-led geoscience teams, moved quickly to classify the zone as a site of elevated magmatic concern. That designation is not handed out lightly. It signals the presence of subterranean activity with the potential to evolve rapidly, with limited precedent to predict its behavior. The idea of volcanic activity beneath the Colorado River may seem implausible at first glance. The area is not known for recent volcanism. Most of the landscape was shaped by ancient forces: uplift, erosion, and sedimentation, not lava flows or pyroclastic surges. But deeper study has revealed that the region's tectonic history is far more complex than previously believed. The crust here is thinner than in surrounding areas, and it rests above a mantle zone rich in volatiles, gases and fluids that lower the melting point of rock and allow magma to form under conditions previously thought improbable. Moreover, historical data, now being re-evaluated with fresh urgency, shows signs of past volcanic episodes in the broader Colorado Plateau, albeit from millions of years ago. Ancient lava fields and basaltic dikes suggest that magma has surged through this region before, even if not in the lifetimes of any human civilization. The possibility now being examined is whether a new magmatic system is reactivating, not from the vestiges of an extinct volcano, but from a nascent one, still forming in the deep shadows of the Earth. This discovery has opened an entirely new chapter in the geological understanding of the American Southwest. Teams are working around the clock to refine the subsurface imaging, deploying muon tomography systems, technology that uses cosmic particles to create high-resolution scans of underground structures. Preliminary models show the chamber expanding laterally, not just vertically, suggesting it is feeding off a broader mantle anomaly. Some fear this could be the beginning of a larger magmatic system developing along an uncharted line of weakness in the continental crust. Compounding the concern is the proximity of major infrastructure. The Glen Canyon and Hoover Dams, downstream hydroelectric giants, lie within potential influence zones if the chamber continues to grow. While there is currently no indication of imminent eruption, the deformation patterns and rising gas emissions, especially increases in carbon dioxide and sulfur compounds from deep fissures, signal that the crust is under stress. These are not yet the emissions of an erupting system, but they are red flags indicating active degassing, a precursor in many known cases to more aggressive magmatic behavior. Ground teams have installed dozens of new monitoring stations, from tilt meters that measure minuscule changes in ground angle to spectrometers analyzing the composition of gases venting through the soil. Every data point feeds into real-time simulation models, attempting to predict whether this magma body will stabilize or whether it will continue to ascend toward shallower levels where it could interact explosively with groundwater. That interaction between magma and water is a particular point of dread for geologists. When magma encounters water-bearing layers near the surface, it can trigger phreatomagmatic eruptions, sudden violent bursts caused by the rapid conversion of water to steam. These types of eruptions don't require a surface volcano to be dangerous. Even a modest intrusion that flashes underground aquifers to steam can tear open the crust with incredible force. What makes the situation beneath the Colorado River especially precarious is the enormous volume of water directly above the potential activity zone. If upward magma movement continues unchecked, the risk of such an interaction, however remote it might seem at present, cannot be dismissed. Another concern lies in induced seismicity. As magma moves, it forces rock apart, generates fractures, and reactivates old fault lines. While the initial swarm of micro-earthquakes was low in magnitude, there is potential for larger seismic events if the pressure buildup continues. These would not be conventional tectonic earthquakes, but rather volcano-tectonic quakes. Earthquakes caused by the fracturing of rock due to magmatic pressure. In a region with aging infrastructure and dense population centers relying on the river, even moderate quakes could lead to disruption. Geologists are proceeding with caution, balancing scientific rigor with the weight of potential consequences. At this point, the magma body is considered intruding but not yet eruptive. It is, however, highly dynamic. The red alert serves as a formal acknowledgement that a significant geological process is unfolding, one whose future trajectory is uncertain. This uncertainty is a driving force behind the urgency. Geology rarely offers fast answers. Rock moves on timescales far slower than human perception. But this case is different. The convergence of multiple high-resolution monitoring technologies, combined with the scale and importance of the affected region, means every change is being tracked with unprecedented speed and precision. Scientists are not merely watching for signs of eruption. They're also trying to understand why this is happening now. Some suggest that shifts in the lithospheric stress field, perhaps related to broader tectonic reorganization in the western United States, may have reawakened ancient mantle processes. Others point to long-term climate changes, where reduced surface loading from diminishing snowpacks and water reservoirs could subtly alter the pressure dynamics in the crust, allowing deeper fluids to rise. These ideas remain hypotheses, but they reflect the scale of the mystery. The discovery beneath the Colorado River is not just a singular geological event. It's a keyhole into processes that shape continents, reconfigure hydrologic systems, and remind humanity of the dynamic forces lurking beneath even the most familiar landscapes. As data continues to stream in from satellites, drones, and ground teams, each new measurement adds dimension to a subterranean narrative still being written. What began as a quiet anomaly, a subtle bulge in the terrain, has turned into a full-scale scientific mobilization, an effort not only to decode the message written in heat and stone, but also to anticipate what that message might become. While the magma remains entombed deep within the crust, it has already changed the surface world above. Policy discussions are emerging. Emergency preparedness protocols are being reviewed, and research funding is being redirected to better understand this phenomenon. For now, the river continues to flow, carving its path through the canyon as it has for millions of years. But beneath its shimmering surface, change stirs, molten, pressurized, and potentially transformative. While the initial shock of discovering a rising magma body beneath the Colorado River sent ripples across the scientific world, the days that followed revealed a much deeper and more intricate picture, one that stretches far beyond the geological anomaly itself. As teams pored over the data, a larger network of changes began to surface, revealing that this was not an isolated event, but potentially part of a much broader tectonomagmatic reawakening of the southwestern United States. Researchers began reevaluating a wide swath of geophysical records, including gravity surveys, thermal flux measurements, and isotopic compositions of gases venting from springs in adjacent areas. What they found was a consistent anomaly arc stretching across a corridor from southeastern Utah to northwestern Arizona, following a pattern not previously noticed. This corridor had for decades been considered stable, far removed from the dynamic processes shaping the Cascade Range or the volcanic fields of New Mexico. But now, isotopic ratios of helium-3 to helium-4 in escaping gases, ratios typically associated with deep mantle origins, told a different story. This pointed toward a mantle upwelling event, a plume or localized hotspot beginning to assert itself beneath the crust. Such upwellings are capable of reshaping not only the physical landscape, but also its thermal and chemical architecture. Unlike typical volcanic arcs formed by subduction zones, where magma is recycled crustal material, a mantle upwelling brings with it a more primitive, hotter, and volatile-rich form of magma. This kind of activity can trigger long-lasting consequences, laying the groundwork for entirely new volcanic fields, or, at the very least, creating extensive geothermal zones. The Colorado River discovery now looked like the tip of a much deeper, more complex geodynamic process whose full boundaries remained undefined. This broader realization shifted the scientific focus from mere monitoring to active exploration. Drilling projects were rapidly proposed to obtain deep core samples from nearby uplifted areas. The goal was to physically analyze the types of rocks currently undergoing alteration, looking for signs of high-temperature metamorphism, mineralogical changes, and the presence of volatile rich inclusions. Such data could reveal the depth and scale of the thermal anomaly and help determine whether it might evolve into a long-term magmatic system or recede back into quiescence. Meanwhile, geoelectrical studies added yet another dimension to the understanding. Magnetotelluric surveys, which measure the Earth's natural electromagnetic fields, detected zones of unusually low resistivity spreading outward from the suspected magma chamber. These conductive zones are typically indicative of partial melts or interconnected fluids. Crucially, the data showed that these zones were not static. They were migrating slowly, particularly toward the northeast. This suggested that the magma wasn't merely pooling in one area, but actively intruding into the surrounding crust along pre-existing structural weaknesses. These structures, invisible to the naked eye, trace their origins to faults and fractures that have existed for millions of years. Ancient wounds in the crust that magma can exploit. Under normal conditions, these faults are dormant, but under increasing pressure, they become pathways for magma, gases, and superheated fluids. In effect, the magma chamber was sending exploratory fingers outward, like roots seeking easier ground. And what the magma touches, it changes. Subsurface temperatures in these zones began to rise gradually. Groundwater chemistry shifted. Springs that had once been cold and clear grew warmer and carried unusual mineral contents, including elevated arsenic, lithium, and rare earth elements, signs that deeper geothermal fluids were beginning to interact with surface systems. The ecological ramifications of this were subtle but measurable. Some aquatic species in the region's springs began exhibiting signs of thermal stress. Native vegetation, particularly species reliant on shallow water tables, showed early signs of nutrient alteration. This complex chemical interaction between deep earth processes and surface ecosystems is what geologists refer to as the magmatic interface zone. It's a transitional region where heat and fluid movement begin to affect the biosphere. Though it may not be dramatic in the way that eruptions or lava flows are, this interface represents a slow but profound transformation, one that alters not only the land, but the life it supports. Urban planners and hydrologists now find themselves involved in what had initially been a purely geological concern. With water chemistry changing and localized heating observed near shallow aquifers, questions began to emerge about long-term water safety. The Colorado River Basin is already under extreme pressure from overuse and climate-driven droughts. A geochemical shift in even a fraction of the basin could necessitate expensive filtration measures or alter the potability of certain groundwater supplies. While current levels remain within safe margins, the trend lines point to possible problems in the years to come if the thermal gradient continues to rise. Infrastructure assessments followed close behind. Seismic risk models had to be rerun with new parameters that included potential fault reactivation driven not by tectonic stress but by magmatic pressure. The probability matrices for structural failure at key sites, such as bridges, dams, and pipelines, were updated accordingly. Glen Canyon Dam in particular came under scrutiny due to its proximity to detected ground uplift zones. Engineers began stress testing for scenarios previously deemed unrealistic. Small to moderate seismic events coupled with regional deformation. What was once theoretical now had to be operationalized into civil contingency planning. Insurance providers and governmental agencies took notice. Risk zones were redrawn. Policy clauses for earthquake and geothermal damage were reviewed and in some cases amended. The Bureau of Reclamation initiated a review of water allocation models, taking into account the potential for temporary disruption to pumping stations or sediment inflow due to unexpected seismic activity or subsidence. In parallel with the response from engineers and hydrologists, atmospheric scientists began tracking subtle increases in localized air composition around the river. Volcanogenic gases, particularly carbon dioxide and sulfur dioxide, can alter air quality long before any surface eruptions occur. Specialized drones equipped with spectroscopic sensors were deployed to follow these gas trails, which can accumulate in low-lying areas and pose a risk to human and animal life. While concentrations remain low, the appearance of these gases at all in this region was enough to warrant continued vigilance. Amidst all this, cultural and historical considerations began to surface. The lands surrounding much of the Colorado River are sacred to numerous Native American tribes, including the Hopi, Navajo, and Hualapai. These communities have long maintained oral histories of the earth breathing or of fire beneath the stone. What once were viewed as metaphorical descriptions are now being reassessed through a scientific lens, as geologists and anthropologists collaborate to decode whether these traditions may have preserved knowledge of past geothermal episodes. This intersection of modern science and indigenous knowledge opens an unexpected but powerful avenue for understanding long-term geological cycles. Some elders recount warm ground patches or the sudden drying and heating of springs generations ago, phenomena that could align with ancient thermal anomalies. In honoring these accounts, scientists are integrating traditional ecological knowledge into their observational frameworks, enriching the narrative and expanding the scope of data beyond instruments alone. All of these cascading effects, from water chemistry to cultural memory, are part of a larger mosaic that now defines the Colorado River mystery. What started as a single magma body has grown into a multi-dimensional puzzle that touches disciplines far beyond geology. It is a case study in how Earth's deep interior is never truly isolated from the surface, and how even the most stable landscapes can harbor latent potential for change. As of now, the magma remains deep, its progress measured in centimeters and pressure gradients. But it has become an active agent, pushing against the crust and forcing new realities into the minds of scientists, policymakers, and local populations. Whether this movement stabilizes, escalates, or branches into new subterranean passages remains unknown. That is the nature of geology. Its truths are measured in fragments and signals, always building toward a story not yet fully told. To advance understanding, several multidisciplinary initiatives have been launched. The first is a subsurface observatory network, funded jointly by federal agencies and private institutions. This network includes not just seismic and thermal sensors, but also AI-enhanced pattern recognition systems designed to detect subtle changes that might elude traditional analysis. Machine learning algorithms are now parsing millions of data points, hunting for correlations that might indicate accelerations or new pathways of intrusion. The second initiative involves active geophysical experimentation, controlled seismic tests designed to illuminate the exact boundaries and density gradients within the magma body. These efforts, while complex, can provide crucial insights into how close the melt is to triggering brittle failure in the surrounding rock. A third frontier has emerged in computational modeling. Using real-time input data, researchers have developed dynamic simulation environments that can project hundreds of potential scenarios, from steady-state intrusion to explosive phreatomagmatic transition. Each simulation offers clues about what indicators to watch for, which regions may become vulnerable, and how long various responses might take to implement if thresholds are breached. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what's hidden beneath the Colorado riverbed? We want to hear from you. Thank you for watching, and see you next time.